Okay, I think we'll get started. Some people might come. Wait. Okay, it's a pleasure to welcome Dr. Panos Charalampopoulos from the University of Turku here today with us. Panos got his first degree from the University of Athens and then moved for his master's to Denmark at the Niels Bohr Institute, and then his PhD he got at DTU Space in 2022. And since then, he's been in Finland for his first postdoc. And today he'll be telling us about TDEs, so the spectra of optical and UV tidal disruption events, almost 2 decades of discovery and questions. So looking forward to this overview.
Thank you very much, Alice, and thank you for inviting me here. I'm very happy to be here and hope we'll meet more of you better after the talk. Yeah, my name is Panos Charalampopoulos, and I'm a postdoc in the University of Turku. Okay, yeah. And yes, I'm going to talk to you about tidal disruption events and specifically the spectra of the properties of the optical spectra of tidal disruption events. And I will also give an intro to the topic for those that are not acquainted with the topic. And hopefully by the end of it, you will know everything about the spectra of tidal disruption events, abbreviated as TDEs. We're going to call them TDEs. Okay. So, we know now that pretty much in all, if not all, hearts of galaxies in the center.
Can I shortly interrupt and ask to press the OK button on your screen?
All right.
Get rid of that.
So it disappears.
Yeah. Good. Okay. So yeah, we know now that in the very centers, in the nuclei of galaxies, live supermassive black holes, and that is true for pretty much all. Maybe at least the vast majority of galaxies harbor a supermassive black hole in their nuclei. And latest confirmation was from the first ever image of the subject of a black hole in the M87 galaxy in the Event Horizon Telescope, but we have a similar one from our own Milky Way. And these supermassive black holes span masses from 10 in the 5 to 10 in the 10 solar masses. And up to now, our way of studying the properties of these supermassive black holes was through active galactic nuclei, or AGN, because things are very bright and they're variable most of the times, and it means that there's big amounts of gas, dust, or whatever that the supermassive black hole accretes, and the accretion produces power. It's very luminous, and we've been for many years now studying the properties of AGN. However, correct me if this estimate is not exactly true, but I think that around 5 to 10 supermassive black holes have an AGN. So what about all the rest ones, which we call dormant or quiescent, which means that there's not enough gas or any material to be accreted, so there is no information coming from those. So here's where tidal disruption events enter the scenario, and we believe we already do, and we believe we can do even more in using tidal disruption events into studying the properties of all this big population of quiescent supermassive black holes. Okay, so yeah, I decided to put in a video. I think it's easy to solve what the tidal disruption event is. It's an artist impression, of course. So here is the incoming star, and here is a black hole. So imagine that something happens in the nuclei that kicks the star into a parabolic orbit around the black hole. So this is what we're going to see here. Let's see if this works. Great. Okay. So as the star approaches, the immense gravitational force from the black hole, the tidal forces elongate the star, and when it reaches what we call the tidal radius, this is where the star gets ripped apart pretty much. And then the debris form an elongated thin stream that self-intersects, shocks, then kinetic energy gets dissipated and material starts getting accreted in the black hole. So that's what we believe really happens. And this is still a topic of debate, what is really the emission mechanism behind these nuclear transients, how exactly, what causes to see what we see. Of course, some of them are relativistic. We have seen some of them jets and even gamma ray bursts, a handful of those. So as I will convey during the talk, these have very diverse properties as well. And they're multi-wavelengths and detect from gamma rays, as I said, to radio wavelengths. And I will get to that soon. Right. So here I'm just gonna quickly try to say what we saw in the video. So this is the star, right? It gets elongated, and then so this RP is the pericenter of the parabolic orbit, which you see with the dashed red line, and this is what I said. This is a black hole, right? And this the tidal radius, which is defined as that. So it's a function of both the black hole mass and some stellar properties, the stellar radius and the stellar mass. So the star gets ripped apart here, and then I think that around half of the debris escape the system into unbound trajectories. Maybe some people say that this could be important for the emission mechanism. This is called like a collision-induced outflow. I'll briefly refer to that scenario later on. The rest get bound to the black hole. They form this thin stream of debris that circularizes, self-intersects, and that causes the energy to get dissipated, and then materials start falling back, and probably accretion starts or whatever other process. And this parameter, I guess I can call it theta here, because it's label it better. It's the ratio of the tidal radius to the pericenter distance, and this defines whether we're going to have a full disruption or a partial disruption. So if this is low, it might be that some part of the star gets ripped and goes through the process that I just described, but the core remains, so it just goes back only to come back again to the pericenter and gets disrupted again and again. So this is what we call a repeating TDE or a partial TDE. And interesting to start, we believe seeing those and show you something later as well about this. So it sounds very spectacular, and you saw in the video how it looks, but in reality, this is what we see. So in the end, it's just some illuminated pixels, and I picked here a beautiful galaxy. Usually they're just passive elliptical globes. But what I want to say is how we discover these, right? Very quickly. So by definition, they happen in the nuclei of galaxies. So with the advent of wide field surveys that scan the night sky every night, so they have their reference images, which is non-transient sky, and this is the reference image, for example, of it's from CPF, and you can see this very bright nucleus. It's the same one like here, right? You see the same image. So they get the science image. Even by eye, you might see that something looks like weird here, very strong. Their algorithm just subtracts the two images and mistake with a different image. Hope everybody can see what I mean. And then you can see clearly that this is just not noise like in the outskirts. There's clearly a transient happening in the nucleus, something that wasn't there the previous night. So that's how we discover them. And I wanted to focus also a bit in the Schwarzschild radius. If you know what it is, means where the event horizon of a black hole lies, and it's a function of the black hole mass. So theory predicted that, for very high black hole masses, so
you can use the leader.
Sure. I try, but got to lag a bit when we're some slides weren't all together, but
Well, the other one
the point. Yeah, sure. And if it's nobody online, I can do it in the screen for you to see. This one, right? Okay, how does it? Great. Okay. Yeah. So we predicted that for masses larger than 10 in the 8, then the Schwarzschild radius would be larger than the tidal radius, which is where actually the disruption happens. So supposedly we shouldn't detect any flare since this happens within the event horizon. So by definition, like the light cannot escape, we cannot see that. And for me, this is one of the most securing observables that make me think that indeed these things are what we believe they are. See, these are the rates. It's a black hole mass. We have different ways of trying to estimate the black hole mass. There are bits, okay, but this is another topic, so part of the scope of this talk. And here is the rates. So you can see that indeed we have discovered several TDEs in this mass range, but then after 10 in the 8, the rates really plummet. So this a good confirmation that we do see what theory predicted.
Sorry, what is R star? You have something R star, your equation, what is R star exactly?
Sorry, which one?
You say R equals R star times that.
This one.
Yes.
It's the stellar radius. It's the radius of the star that it's informing. Yeah, so the stellar mass, the stellar radius, and the black hole mass, which is the tidal, what we call the tidal radius. Which is many times mistakenly written as the tidal radius of the black hole, but yeah, as you see, it's not just a function of the black hole. Okay, so TDEs were predicted, like the first paper talking about TDEs is this paper by Rees in Nature, and the prediction is that after the disruption happens, this will form a classical thick accretion disk around the black hole with temperatures of 1,000,000 Kelvin, hence emitting the X-rays. And indeed, this is where we started discovering TDEs, the X-rays, and later on with Galax, there were some UV ones, which was also predicted that the SMB would be bright in the wavelengths of Galax. But then came the era of the wide field optical surveys since 2010. And then we found something that we were really not expecting. We started discovering many TDEs in the optical, and some of them are also emitting the X-rays, but some of them are solely emitting in the optical and the NUV. And yeah, so this challenged our view, the theorist view at least, of these events. So a family of scenarios popped out, which they still keep coming. And I think the most famous one, at least, and the most accepted one, is this reprocessing scenario, where the idea is that there is an optically thick envelope forming around the accretion disk based on super accretion and optically thick outflows or whatever. The idea is that there is a photosphere around the accretion, so the X-rays from the accretion are reprocessed in this envelope to optical and UV wavelengths, and then kind of get these observables that we see in optical TDEs. And later on, this was updated, upgraded with viewing angle predictions, where we try to explain why some TDEs are only X-ray bright, so this should be viewed like a face-on through a jet escaping from a funnel. And if we're looking edge-on, we see only optical emission because everything is reprocessed, and like intermediate angles could reveal both X-ray and optical emission. Then it's this shock and stream collision scenario that suggests that the optical and UV emission is coming from this self-crossing of the tidal stream that I talked about earlier. When the debris, this elongated debris stream hits its tail in a way, this causes strong shocks, and optical and UV emission is coming from there. And this is another prominent scenario. Then, more recently, it's this collision-induced outflow scenario that, in my view, it includes both the aforementioned scenario, where there is this collision-induced outflow that I talked about coming from where the shock happens, when the collision of the debris stream happens, and then the black hole is offset to this collision, and this reprocessing envelope, its center is the collision and not the black hole. So it's a combination of the two things that I talked about before. And even more recently, this cooling envelope scenario that really tries to explain some observables like constant colors and constant temperature evolution that we see in the TDEs, which is weird, or late time plateaus in the light caps. So what I want to say with this is that the emission mechanism is still an open question. We're not there yet. Some things we can explain, but others are still elusive. And each new TD brings something that maybe challenges our view, because they're not so common. They're rare. They're much rarer than supernova. And only recently, after ZTF, we started really getting to these rates. Now we have identified, since the first one in 2008, we have 100 candidates, and some of them, what's the expression in English about those? Because many of them the classification comes much later than the peak. There's just one spectrum, and because of the light field properties, we believe that this must be it. But they're rare, and they're even more rare, the ones that we have discovered early on, even before peak. And the fact that they're in the nuclei makes it harder to discover, because there will be many things that cause some variability. But yeah, we have around 100 candidates so far. And so very quickly, some photometric properties, let's say, they have these optical QVTTs, they have black body radii of this range with receding photospheres. They have temperatures of 10,000 to 50,000 Kelvin, and see that they usually are constant, that we see also in the optical colors. They have very blue continua that usually, at least at the early times, peak in the near UV, and their spectra are dominated by broad emission lines of 10,000 kilometers per second. Yes, so I can now start focusing on the spectral properties. So in early work by IAASARS, we understood that these emission lines are of hydrogen, so Balmer lines mostly, and helium, and specifically this helium-2 4686. That's a very different line to this. So Balmer lines and helium-2, sometimes helium-1 5876 are here, but this is it. And these lines are photonization and recombination lines. So, and as years passed, we kept, bringing new TDs that kept showing the same lines. So we're discovering more and more events and putting them into this continuum of hydrogen to helium rich, with some of them intermediate, so both hydrogen and helium in the spectra. So that was the early idea. And so one new thing we discovered as more TDs were getting in the sample and we were getting early spectra, as I said, is that sometimes we saw these early profiles that were blue shifted compared to the rest, like both in helium-2 and in H-alpha sometimes. And they had this kind of abrupt rise in the blue and extended skewed red wings. And so this was something new. And this is something we believe we understand within the reprocessing scenario that I talked about. If everything is embedded in an electron scattering dominated photosphere, this paper by Roth and Kaysen made some models, and they, based on, again, optically thick outflows and electron scattering, this can explain the blue shifts and the red skewed wings. And you can see here a comparison with a model, and this from another paper that nicely reproduced these profiles 9 days before the peak here. So that's good. But another thing we discovered with time is that things are not so simple. It's not just hydrogen and helium in the spectra of TDs. So, in this paper, Yorgos Leloudas, we kind of identified that, what's the word? Now the community accepts this as a fact that there's a class of TDs that show these highly ionized nitrogen and oxygen lines in their spectra with for these lines we call them Bowman lines, and they are caused by this mechanism called the Bowman fluorescence mechanism. So the most prominent line of this mechanism, at least in the optical, right, is this nitrogen 3 line at 4640 angstrom, which unfortunately is super close to the helium-2 line, 4686, and most of the times are blended in the spectra, and another one at 4100 on top, literally on top of H delta. So we usually see these lines in TDEs that have both hydrogen and helium, and the helium is not surprising because you need helium, you need to ionize helium-2 and then be recombined in order to trigger the Bowman mechanism. So, and this also means that we need a source of extreme UV radiation that ties well with the accretion happening in the center, because you need this type of emission in order to ionize the helium-2. And so here's how a closer look to this heavily blended region looks like. And here, for example, you see we're fortunate enough that CD was very bright, so we could kind of see the two distinct peaks of nitrogen 3 and helium-2, but that's not always the case with low resolution spectrographs, right? It could be that many times it just comes as a blob. So in order to blend the complicated process, you have to make some assumptions, apply things based on the velocity weights with other lines, etc., etc. But a good, a robust way to identify a Bowman TD, as we call them, is that, you know, this line here, it doesn't make sense that this is just H delta. So it's already kind of stronger than H gamma. So we know that probably it's also this other transition of nitrogen 3 that I talked about that booms out in this region of the spectrum. And so if you're not convinced, here is I'm going to show you the spectra of a repeating TD that I talked about before. You can see we had the first peak, we saw this nice normal TD, and like 2 years after, we have a second transient, the same nucleus, and we have seen nowadays 2, 3 of those events. So we do believe they're coming from the same star. But so this one, I just wanted to show in order to see that, for example, this doesn't make sense that this is just H delta all of a sudden. So we know that we have nitrogen 3 both here and here. But yeah, very interesting event, this one.
I just want to ask you, for example, I heard about this Bowman fluorescence mechanism a year ago in TDEs again, but can you explain a bit more what is this Bowman fluorescence mechanism?
So I think what happens is that you have to ionize helium-2 to helium-3, and then when it recombines, it emits photons, and that needs extreme UV radiation. So it emits photons that happen to have similar transitions like this nitrogen 3 and oxygen 3 lines. There's a plot, maybe I can show you after, typical plot with the transitions. So it just happens that there's a photon of the same wavelength that triggers this mechanism. Then you have a cascade of oxygen 3 and nitrogen 3 lines. But I can look at it after. But yeah, that's the main thing. You need the helium-2 to be ionized and then recombined, and the photon is emitted when it recombines, it triggers.
Okay, maybe it needs radiation mechanism that's close to these temperatures than the force. I was wondering why you can say in 88, for example. Obviously, it's sensitive to the temperature of the disk.
Yes, and there is a new class of events that in the beginning we thought they're TDEs, that now called Bowman fluorescent flares, that we believe there's some type of sudden AGN activity, because they look like transient, right? You might have some small variability, but then suddenly you have a very long-lasting flare that has has these lines, those has nitrogen 3, shows X-rays most of the time, and these are rare as well. So Bowman fluorescent flares is also kind of recent thing, and we believe it might be some AGN. In the beginning, people thought they're TD, but we're not sure.
In this paper, you showed how many days after the event. So from last telescope, so I wonder how many days after you can get such good spectra, because I mean, it dies exponentially, so probably we're talking about a week or something. That you can get this.
Depends on how far it is, right? So it depends really on the apparent magnitude flux, I think. So, and on the telescope. So if you have access to I don't know, an 8-meter telescope, you can very well. Yeah, that is a combination. But they usually last, they can have like a week to a month time scale to rise to the peak. And then they can last from, I don't know, a month, 3 months. But again, that depends on also how close it is, how long you can go.
So you need to be fast here.
Yeah, yes. Yeah, so adding to the diversity in the same heavily blended region of around 4,500 angstrom, it was discovered this forest of singly ionized high iron 2 lines, and this reminiscent of narrow line Seyfert 1 galaxies viewed face on. These lines need a compact accretion disk and high density optically thick gas in order to be excited. And we believe we see them at the spectra of some TDEs. And this ties well with the fact that these TDEs are they show simultaneously strong X-rays, so it could be indeed like they're viewed face on, but I will talk more about this. Later on, another very interesting event was this one from 2018 that you can see after a while, and here you can see the faces compared to peak, right? Always indeed these refer to peaks based on your question. It developed this clear double peak Balmer profiles in the spectra, both in H alpha and H beta, and this was attributed again viewing an accretion disk probably to intermediate angles. It also showed mild X-ray emission, and it's not the first one that shows kind of a double peak-like profiles and mild X-ray emission, and not the last. Even more recently, there was a TD that was claimed to have a triple peak in the Balmer lines attributed to viewing an elliptical accretion disk. That's how we try to explain the data set. And the latest addition to the collection is this. It was a very close liner galaxy, so not an AGN, but a liner type host and merging with another galaxy, very close, probably the most close by optical UV-TD to date. And so I followed this up, I wrote a paper on it, and on top of this early, very broad and outflow dominated H alpha profiles, we saw now this thing here for the first like 10 days, which is the first time we see something like that in the profiles. Then it went away, it never came back until the event faded. So that was very puzzling, and our question was, why we haven't seen it in another TD. So we explained this as hydrogen and H alpha fast moving towards us, maybe due to indeed like collision-induced outflow happened to be directed towards us, because this line is blue shifted around 10,000 kilometers per second from the rest wavelength of H alpha, and it ties well with the early outflow, strong outflow scenario. But yeah, I'm not going to focus on a single event, but always check the paper. And so I'm getting back to this QIZ event. It's the one that I showed in the beginning with a nice spiral galaxy. So this thing, here is some mid-infrared data. This is the WISE data. You can see before the transient happened, this is the transient. Okay, it looks normal TD light curve. But then this is not the first TD that does that. We see from them triggering a huge infrared echo that goes on for here. You can see, and this really huge. So people studying mid-infrared, so it probably means that the TD itself just heats up some dust that exists in the galaxy, and then this manifested as an echo. So this is interesting. And apart from that, this TD showed delayed X-ray emission, like a year after it has faded. So then some people went and got some spectra, and what you see is exactly the host galaxy spectrum. There's no TD left in there. But it is full of these coronal lines, like of iron, and iron 7, iron 10, iron 11. And these events, they have been studied in some early papers, mostly of Stephanie Comosa, that she was studying these extreme coronal line emitters. So these were just galaxy spectra in the optical, but populated by these coronal lines. And it was from 2010 or earlier on, I think. It was a speculation that this would be something triggered by a TDE. So through this one, we have kind of a first direct confirmation that, after the TDE happened here, so this coronal lines comes up, and this needs an X-ray source in order to trigger these higher emission iron lines. And well, this event didn't stop surprising, and even more recently, like some months ago, we understood that this X-ray emission is not just some continuous emission. So from this paper of McNichol, they understood that these are quasi-periodic eruptions, which is kind of a new thing, if I understand correctly. And this means frequent, within hours, X-ray flares happening in the nucleus. And again, when this thing started being studied, the X-rays, it was one scenario that they might be triggered by TDEs. So this one gave again a clear kind of indication that indeed TDEs do power QPs. I don't know if it's all QPs powered by TDEs, but definitely doing. So it happened completely randomly. It just had some standard time to study late time accretion of TDEs, and just within hours they got these images that can clearly see that something happened. So they went on all this nice data, and this is happening now, like after 5 years from the TDE happened, you see this thing in the nucleus. Okay, so said many things and connected TDEs with many things, right? And this indeed still they're complicated. They're complicated, and each new event can bring in new things that we didn't know before. The challenges are viewing. So how can we understand more? Because of the emission, well, one way is through modeling, right? But there haven't been many works in the spectra of TDEs. And the ones I know of are, there's this tool from Roth et al. In 2016 and Parkinson et al. In 2022, where they managed to reproduce some qualitative figures like the Bauer lines and the helium-2 line, but they failed in other aspects, like none of these codes could reproduce Bauer lines, even if they tried, or the profile shapes looked oddly shaped, or helium-2 being disproportionately strong to H alpha, or needing kind of unrealistic optical depths in order to reproduce the spectra. But as I said earlier on, we have one paper from modeling. We believe we can explain now why early on we see many times blue shifts, the lines being blue shifted and having these weird profiles based on the reprocessing scenario. So then what about sample studies? That can also help. So I wanted to show you this. I saw it also was this nice conference in Crete in the beginning of September. I think it was the first one that was a full week dedicated on TDEs and nuclear transients. So there were 94 talks and posters in this conference, and only 3 of them had spectra in their title, right? So this is still an understudied field, I believe, the spectra of TDEs. So in terms of sample studies, well, the only one I know of is my first paper ever, first paper of my PhD. So I believe we can do better than that. But back then, we decided to study 16 TDEs with well-sampled, like that we had good spectra. If there were early spectra, it was better, but we needed high signal-to-noise spectra. And we put a cut in events for 2019, so we could make also proper host galaxy subtraction, because there's another thing you need to do. I'm not going to focus on that right now. So we wanted the events to be gone when I started the study. So I'm going to focus here on H alpha, as it is the most prominent and also the less blended line in the spectra of TD. So it's safer to draw conclusions from. Okay, so here I'm plotting the evolution of the full width half maximum with the line width of H alpha as a function of time for the sample, and I color code so the blue ones, the black ones, are events that also show bound lines in their spectra, while the orange ones didn't show bound lines. So we clearly see that the bound rich events, let's say nitrogen-3 rich events, show lower velocity widths than the rest. And this is interesting because in a photometric population study, we have more of those. This class of hydrogen and helium rich, what they call bound TDEs here, these green squares, we see that they have systematically lower black body radii and higher temperatures. So if the line widths were set by the kinematics, and if the line emitting region is also smaller for smaller photospheres, then Clarion mechanics, we would expect that the boundary TDE should have higher velocity widths than the rest. And here we see exactly the opposite. So we believe that this can be another indication of electron scattering, that the line widths can be set by electron scattering, and as I'm going to show several times, this cartoon from Ralph et al. Providing kind of a stratified photosphere embedded in an electron scattering photosphere. And this is also in line with other observational sample studies, the first ever spectropolarimetric sample study of TDEs of X-supervisor, showing along with the reprocessing and electron scattering dominated photosphere. Okay, so back to H alpha, and here's the luminosity of H alpha as a function of time for the sample. And one thing rises and drops, but one thing we noticed is that for many events, it seems that so the 0 point is the peak of the event, but for all those, because we have all the events, for all those, many of those were discovered after peak. Okay, so it's the discovery for the older ones. So we saw that for many events, the H alpha line peaks much later than the optical light curve. And here's a kind of better visualization of that. So the field circles are the photometry, the light curve, and the whatever markers with the dust line is the H alpha luminosity evolution. And on the left is events that were discovered before peak, on the right are events that were discovered after the peak, so you can only put a lower limit in studies. So this, like it looks like that H alpha lags the optical line curve, right? So this lags will be of 1 from 7 to 40 days. And we keep seeing that in newer TDEs that are after this sample study of mine. And here again, I color code in the same way, and I'm plotting this lag times as a function of the peak of the black body, the optical photosphere. And so one thing we see is that this bound rich TDEs seem to show smaller lag values in the H alpha. That, and this was kind of reminiscent of what we see in AGN studies brought by reverberation mapping, that we see echoes of the lines in the broad line region. And so based on this kind of physical scenario, that would mean distances of in the 16 to 10 to 17 centimeters. But we said these have like photospheres, optical photospheres of 10 to 14 to 10 to 15. So this means that this material should be 10 to 100 times further out than the optical continuum. So in AGN, that's okay, because this pre-existing material structures around the supermassive black hole. But for a TDE, it's a bit hard, I think, to how material could have gone there so far, so early before the photons. And so we discussed several possibilities and scenarios in the paper. One idea is that it might be that there is material, but of lower electron densities, because in AGN these electron densities are like 10 to the 10, 10 to the 12. So the combination time of meeting the line is considered to be instantaneous. So one suggestion was that with from lower densities, it might take more time to meet these lines. And we also discussed that this material around from this collision induced outflow happening early on. So that would prove a way, that could provide a way to have material further out, but still this could be this could provide the time lags that we see, and it would be nice because Bowen TDs need supposedly higher densities around them. And since there's a lower lags, that would mean higher electron density, so that would tie nicely in a way, but there hasn't been any proper modeling on all these things, right? So here I'm showing, again, this is the luminosity of H alpha on the y-axis as a function of the black body temperature and radius. And these values were taken from the literature, from all these photometric sample stats. As I said, they were interpolated in order to match our spectral epochs. And so what we see this trend. It looks like, for smaller radius, we see fainter H alpha. With the lower temperatures, we see higher H alpha. And I'm going to focus first on this right one. So this is in line with, again, theoretical predictions. This paper of Roth et al. I keep referring to the same papers because, as I said, there are not more like spectral modeling studies. But this paper did predict that for basically the reprocessing scenario method, for smaller reprocessing envelope radius, then the H alpha emission should be suppressed. That's what we see here. And indeed, this linear potentially monotonic relation is exactly what we see. And so another diagnostic that can test against these models is the ratio, the luminosity ratio of the helium-2 over H alpha. And we see the ratio getting stronger for smaller optical photospheres, which again is in line with its predictions. And they suggest that for smaller photospheres, H alpha emissions would be suppressed because it's self-absorbed in most area, while helium-2 is thermalized into greater depths and emitted over a greater volume as well. So that was a nice result, I think. So this indeed points to a stratified TD photosphere where helium lies deeper on the hydrogen photosphere, if you want to call it like that. And so in terms of the temperature, don't have much to say. We see that like kind of below 30,000 Kelvin, or actually above 30,000 Kelvin, H alpha really fades. And believe that this could be an ionization effect, but this means again that the line emitting region should be in a way correlated with the optical photosphere, and whatever happens to the photosphere affects the line emitting region. So being, I don't know, 100 times further out, maybe doesn't work in this way. But I think this is interesting. Let's say this is the helium-2 over helium-1 ratio plotted as a function of the black body temperatures. And what we see, it looks like there's a trend that gets fainter for lower temperatures. And for these events that have the lowest temperatures in our sample, we can only put an upper limit because there is only helium-1 and not helium-2. So we believe that this ratio might probe the ionization state of the debris. So for low temperatures, helium is not ionized sufficiently. So that's what I can say about this. Okay, so here I'm showing you the same plots that I showed before, but I'm having a color code again where we're dividing things into some subcategories. So we have this hydrogen and helium TDs that many times show nitrogen lines, and other times show this forest that they talked about, iron 2 lines, and sometimes also oxygen 3 lines combined. And then we have plain hydrogen events, and I see double peak for these events that I talked about, that they do so double peak sometimes, and mild X-rays, and this I call plain, but this one we can just call it hydrogen TDs, which are the red and orange here, and the others are the blue and cyan. And the fact that there is a dichotomy, we know it from the plot I showed before from photometric population studies, right? But what we wanted to do is to try and maybe explain all this diversity, these different spectral properties based on this reprocessing and viewing angle dependent scenario. So we try to take every information and try to put everything together. So, and then the only natural thing apart from the spectral properties was to put the X-rays into that, the X-ray properties. So we've seen that only 1 out of 6 nitrogen-3 events showed X-rays, while both of these iron-rich events showed strong X-ray emission, while the hydrogen-rich, this double peakish ones, had mild X-ray emission, while the other ones didn't show. So we try to, as I said, put this into perspective. And so we suggest in this paper that it might be that this class of events, these iron-rich events, are viewed face on, like the non-1 galaxies, and the nitrogen-3 Bowen-rich events are viewed edge-on, so everything is reprocessed. All the X-rays are reprocessed to optical UV, and this tells us that the Bowen mechanism needs higher densities, so a tighter photosphere and more dense would make sense. And then the plain hydrogen events with the larger photospheres mean lower densities in the photosphere, lower optical depths, which can allow us sometimes, based on also the disruption properties, because this is also something that every time the star can be in a different orbit, it can, all these things that I talked about in the cartoon before can be in different distances, and we don't know how this can manifest in the observables. So it could be that these lower density photospheres would allow us sometimes to see peculiarities of some mild X-ray emission. So this is what we suggest, and it should be renewed with newer events, but some of them are, we have nice spectral coverage even before peak. But yeah, I haven't found the time to write a number 2 paper on that, but hopefully I will. And very quickly, getting to the end of the talk, I wanted to also talk about UV spectra. Since I'm talking about optical and UV TDEs, much harder to get. Yes, we only have HST spectra, and these are not these together, but now we have managed to gather kind of a nice sample. The dream would be to get a pretty big spectrum also with HST and properly sample the evolution of a TD, but yeah, it's harder. So one thing that might be interesting from the UV spectra, among many, I guess, is this ratio of semi-forbidden nitrogen to semi-forbidden carbon. And in this study of the Young et al., they found that 3 LTDs showed a lower limit of 10 in this ratio. So why is that important? Because this ratio proves to be very robust into like pinning down the abundances of the material in the line in the emitting material, because they have similar critical densities and excitation energies, unlike the optical nitrogen-3 lines that they really depend on the specific gas conditions. So since this ratio can prove their actual abundances, this can allow us to constrain the stellar mass. So in this paper of Brenna Moltler et al., they kind of visualize that. So you see that for this upper limit of 10, which you can put here as the abundance, then you can, in the same way, put a lower limit on the stellar mass, or this specific case would be 1.37 solar mass. So it's important because it can provide an important diagnostic to study the stellar properties, to study the properties of the star, and this means that we could do that broad stellar populations in the nuclei of other galaxies. And so, last thing I wanted to show to you, this never stopped surprising us. So recently there was a TD that was discovered pretty big, it's 24 WSD. So I decided to take up the follow-up of this one. So I started gathering some spectra, like it happens many times. It proved that, like a week after it got classified as a TD, it reached the peak. And back then it was what we were talking before, right? It was around 18.5, which is good because sometimes we discover them even lower. And, if it peaks here, there's pretty much nothing you can do. So I was excited, like, hey, it's pretty peak, and maybe do nice things. And then it's the peak at 18.5. So, yeah. But still, I kept getting spectra. And this is very hot, and these are hot in general, but this was a 30 to 40,000 Kelvin, so one of the hottest optical and UV TDs. So that's interesting. No X-rays. I also triggered Swift and started gathering like near UV photometry, and we started seeing this typical, early, kind of also elusive and maybe broad lines, helium-2, H-beta, H-alpha. But then in this NTT spectrum at 33 days, saw something interesting. It looked like first of all, we really confirmed that there is nitrogen-3. As I said, it was already an indication from here, from the H delta. Well, here you can see how blended things are, right? That's what I was saying, that for low resolution spectrograph of entities or the observed conditions all combined, then you can just have a big blob which go and try to study the properties of its line there. But then we saw that the two nitrogen-3 lines seemed like having different widths than the H-alpha or the helium-2 or whatever. So that was interesting. I thought it was worth trying for a DDT with a shooter, and that's pretty much the figure from there. And week after it got accepted, so that was good news. So the plan is to get these 3 spectra. I have got the first one, and now we're after here, but it happened that this time there is a gravity plus VLTI running there, so can't still get the spectrum, but hopefully soon. And I really didn't have time to properly study and see what we see. We wanted to also see if we can resolve the oxygen-3 lines in the near UV, and it looks like the other lines start narrowing as well. But yeah, that is the spectrum, but it's very fresh. It just reduced it. I have to play more with the reduction and things. But yeah, I just want to say that, every event can bring something new and interesting in, and the more time we have to get spectra, the better it would be in denser coverage, the more things I think we can, because imagine if we lost the spectrum, we wouldn't see this sample transition. So this is it. Thank you very much, and I'm happy to take questions or discuss or whatever. Thank you.
Thank you, Panos. Time for questions.
I asked too many. I have one more. So I was wondering about this line that you showed in 3799. Is the line to explain, correct? The one you did, the liner,
the liner, yeah.
A liner.
Yes.
So I was just a very naive question in a sense that